So, let us start with the segment 4 of module 2. Here we will be talking about conditional expectation as a variation of what we have already looked at. So, I call it conditional expectation 2. What is the plan for the segment? We will just revisit this branching process that we talked about in the last segment. And then in order to understand this branching process, we particularly want to know the expected number of children at an arbitrary generation I, and to understand that question we will introduce this notion of conditional expectation version 2, if you will. We will describe some properties of that notion, and then get back to the branching process and try to understand that question. So, let us a quick reminder of the branching process. So, we start with one mother, if you will, and that mother gives birth to some number of daughters, and those daughters become mothers and give birth to their own daughters, and so on and so forth. And the way we are modeling it, each mother gives birth once to a random number of daughters, and the random number is chosen from the binomial distribution with parameters n and p. Each mother, we know on expectation, gives birth to n times p children. So, even you also know, for example, if there are k mothers in one generation, in the next generation the expected number is k times n times p. But what we do not know is how to generalize it to an arbitrary generation I. Okay. Intuitively, the first generation there will be np daughters on expectation, and those np in turn will produce np, each will produce np daughters. So, it will be np raised to the power 2 in the second generation, and so on and so forth. So, in arbitrary ith generation, intuitively it is np to the I. We want to make sure that we can we have a clear formal basis for this intuition. Okay. So, with that brings us to this notion of conditional expectation. And the second version, in which we define this expectation of y given a random variable z. So, this expectation of y given a random variable z itself is a random variable, and it takes the value expectation of y given a specific value of z, this lowercase z, whenever the random variable uppercase z takes the value lowercase z. So, if you think of the sample space as being divided into regions, so with various regions corresponding to various values of z, each region, if you condition on that region, you would get an expectation of the random variable y, and that expectation itself is now a random variable over the entire sample space, right, and that is this expectation of y given z. In a similar fashion, we can also view the probability of some event E over this random variable z. So, going back to this picture again, z, let us say, divides up the sample space into regions, and in each region you have a certain conditional probability of some event E. Okay, and that now becomes a random variable, and that is what we will denote by probability of E given this random variable z. So, as we talked about, this E of y and given z and probability of E given z, they take on different values based on the values taken by z, and thus they are random variables. Let us work out a formula for the conditional expectation in terms of this conditional probability. We are asking what is the expectation of y given z. Now, it is an expectation, so we would try to work through sum through all possible values of y, and in each case it is very simple. We just use the conditional probability of y taking the specific value of lowercase y conditioned on this z. So, it is a very natural formula that we can have for conditional expectation of y conditioned on z. So, let us work out a simple example. Hopefully, this will be helpful in making the idea concrete. So, recall we have already talked about this example where we have two random numbers generated uniformly at random between 1 and 10. Okay, so, we call them x1 and x2, and capital X is the sum of x1 and x2. So, now we ask what is the expectation of this capital X given this lowercase x1. Okay. And we can apply the formula. So, this is simply the formula that I had mentioned in the previous slide. You are looking for the expectation of x. So, you have to run through all the values that x can take, and then we weighted by their individual probabilities, of course, each conditioned on x1. Okay, whatever that means. Okay, let's see what that works out to. So, now what are the values that this uppercase x can take? Well, it is hinging on x1. So, if x1, whatever x1 takes, it can take a value x1 plus 1 all the way up to x1 plus 10. So, this lowercase x therefore runs from x1 plus 1 to x1 plus 10, and of course, here you have to sum the individual elements weighted by their probabilities. Now, what is this probability that x equals this lowercase x conditioned on some x1? What is this basically talking about? So, this uppercase x has to take on a specific value x conditioned on the value of x1. Okay. In other words, when will that happen? When x2 takes the value of, so basically what should happen is x, another way to write this is x should be equal to, this lowercase x should be equal to x1 plus x2, right. And for that specific value of x2, for the event that x that happens when this x2 takes this value lowercase x minus x1. What is the probability of that specific event happening? It is going to be 1 over 10. So, this whole probability is basically 1 over 10. So, this is so now you can expand this out. So, if you work out this sum, what is going to happen over here? You are going to run from values of x is going to range from x1 plus 1 to x1 plus 10. So, you are going to have x1 added 10 times, but each of those times it is going to be weighted by 1 over 10. So, you are going to have an it is going to average out to just x1 plus this second you are adding a quantity here x1 plus 1 all the way to x1 plus 10, right. You can think of it as another I, if you can think of it as a value I running from 1 to 10 or rather x2 running from 1 to 10. That also will take the values weighted by the probabilities 1 by 10. So, the second term, if you think about it, it is this basically summation 1 through 10 x2 times 1 over 10, that is going to work out to 5.5. So, what is it ultimately going to be? This expectation is going to be x1 plus 5.5. You can work out the details, but let us look at the intuition here. We are asking what is the expectation of uppercase x given some lowercase x1, and this is basically, remember, this is a random variable. So, you on the right hand side you cannot have a constant, you will have to again have a random variable on the right hand side. That random variable is x1, and over and above that random variable you are going to add a 5.5, and that makes a lot of sense, because now whatever your x1 value is, your x is going to be on expectation 5.5 plus that original value of x1. Okay. So, this hopefully the intuition at least is very clear. I would recommend that you go through the details to convince yourself. Okay. Here we notice that this expectation of x given x1 or any of these sort of conditional expectations, it's sort of a random variable. So, it's a meaningful question to ask is what is the expectation of the expectation of x given x1. So, what will that be? Well, let us work it out in this example. What is the expectation? Well, we already worked out that expectation of x given x1 is x1 plus 5.5. So, we can apply plug that into the interior of this expectation, and now we get two terms. So, now so we can apply linearity of expectation. So, it is going to be expectation of x1 plus the expectation of 5.5, which is going to be just 5.5. What is expectation of x1? It is going to be again 5.5. Remember, it is a uniform random number between 1 and 10. So, it is going to be 5.5. It is going to work out to 11. And if you think about it, it is also the expectation of uppercase x. Why? Because uppercase x is x1 plus x2. So, expectation of uppercase x is expectation of x1 which is 5.5 plus expectation of x2 which is 5.5. So, that is also going to be 11, and so there is this, when you take the expectation of the expectation, what you end up getting is just the expectation of the original random variable x. Okay. So, this is true from the example. The question is, can this be generalized, and as you would expect, yes, you can generalize it. So, in general, what we are claiming here is, if you remember, expectation of y given z is a random variable. If you take the expectation of that random variable, you get back expectation of y. So, I am going to give you an illustrative way to look at it. At least this helped me to look at it and make some sense out of it. So, maybe this will help for you as well, and then we will formalize it as well. Okay. So, what I am going to think of is this experiment. So, we have a geographic area and we are looking at people in this geography. So, this is, think of this sample space as people in some region, and the experiment is to choose a person uniformly at random, and each person that you choose, y corresponds to the height of that person and z corresponds to the district number. So, you have various districts, let us say, in this region. So, now what you can think of is expectation of y given z equal to 2 is basically restrict yourself to the second district, and you ask what is the expected height of the people in the second district. So, now we ask, okay, in this context we ask what is expectation of y given z, the expectation of that. Okay. If this is an expectation of a random variable, right. Let us look at what this is about. Each of these regions has a certain z value associated with it, and each of them has a value of the expectation of y given that z value. So, when we want to take the expectation, what do? For each of these regions, we take the expectation of y given z equal to that particular z value, and then we weight that by the probability that z equals that value. Okay. And we sum it over all possible z values. Okay. That will give us the left hand side. The way to think about it is, you look at each one of these as a district, you look at the average height for each district, but then you weight it by the size of those districts. That is what you have on the left hand side. Now, let us play this intuitive thing. What happens if someone comes and redraws the districts? Some politician comes, redraws the districts. So, now it is no longer z, it is z prime. So, now again the same, you can still ask what is the expectation of y. Now, let us say given z prime. Okay. So, that should be a z prime over there, and intuitively again, now what you are doing, you are doing this weighted height of people across this new districting, and there is some intuition that should tell you that, look, these are essentially the same. Okay. These are just weighted slightly differently based on two different politicians and whatnot, but essentially they are referring to the same quantity, and that is what is on the right hand side, expectation of y.
Only happens because expectation is linear.
Yes.
Intuition.
Intuition. Yes, that is correct. So, let us work it out more formally now. Let us try to work out this intuition. Okay. So, let us restate the claim. So, what we are claiming is that this left hand side, we remember we worked it out as this formula, expectation of y given specific values of z weighted by the probabilities of z taking various values. Okay. And on the right hand side, we want to claim that is equal to this expectation of y. All right. So, we will take the left hand side. We have this expectation of y given a specific value of z. So, we can expand that out. We have a formula for that. So, that is basically expectation of y. So, you have to run through all possible values that y can take and weighted by these conditional probabilities. Sum them up and weight them by the conditional probabilities. I am just restating that here. So, now what we are going to do is, so I am going to interchange the summations. I am going to bring the summation of y outside, and I am taking this summation of, this probability of various values of z inside the inner summation. So, I get this expression. Here what are we doing? So, this is basically, let us go back here. What we have here is a conditional probability of y equal to specific value of lowercase y conditioned on this value of z times the probability that z will take that value. This is simply nothing but the probability of y equal to y intersected with z equal to z. This is just conditional probability formula. Now, how do we get this term?
Summation over z.
Yes. So, this is summation over all z. So, this is what property? Law of total probability, right. So, you are considering all values of z. So, this is going to cover the entire sample space. So, this is just the law of total probability. You will get summation over y basically weighted by the probabilities of various values of y, and this of course is nothing but the expectation of y.
What was the initial expression for E of y given z?
E of y given.
You can't have z equal to z in that, right? Like when you do, like you can't say that sigma E of y given z is sigma y.
Wait, let's go back. Are you talking about this entire?
I'm talking about the guy inside the first expectation.
So for that we have this other expression.
Yeah. So how did we convert that into z equal to z expression in the?
Let's look at that. So, but now we are looking at this expression, expectation of this random variable, right. So, now think of it this way. Look, there are these, what is this? This is an expectation of a random variable. So, what is inside is a random variable, okay. What is that random variable going to take on? For each district, if you will, each event, if you will, it is going to take on a value, okay. What is that value? It is going to take on expectation of y given that specific value of z. So, in this district, it is going to take on the value of the height of people in that district, okay. That is expectation of y given that district number is 2. For each district, it is going to take on a different value, okay. So, now that is this random variable inside E of y given z. So, when we take the expectation of that, we sum up all those values. So, do not for a minute forget that there is this expectation, you are summing up over all these values, but then you have to weight them by the district probabilities. So, now let us go back to the branching process. This is interesting because now what we have done is we have built the machinery to address this question with this branching process. So, now we want to know at an arbitrary generation I, what is the expected number without conditioning on the previous generation. If we know the previous generation, we know we already had the tools and techniques to answer that question. If we cannot condition on the previous generation alone, what do we do? Let us see how we can work this out. So, let us use the random variable yi to denote the number of females at the end of generation I. So, now we can ask what is this is something we already know how to do, this should not be too surprising here. What is the expectation of some yi, that is the number of females at the end of some generation, given in the previous generation you had some certain specific number. So, remember this is a very specific number, this is a random variable, but this is a specific number. So, then if you know that in the previous generation you had a specific number of females, then you know that each one of those females is going to have on expectation NP daughters. So, what is the total number of daughters at the end of the ith generation? It is the number of females in the previous generation times n times p. Okay, this is should be straightforward. So, now let us hang on to that. What we want is expectation of yi, and notice there is no conditioning here. We just want to look at the ith generation and ask how many, what is the expected number of daughters at the end of the ith generation. And this is where we go back to this claim that we have here. Okay. What we are looking at is the right hand side, and I am going to apply the left hand side. So, now we know that expectation of yi is nothing but the expectation of yi given yi minus 1. Okay. This is just applying that claim that we worked out just now, just in the opposite direction. And this inner part, expectation of yi given yi minus 1 intuitively is nothing but yi, whatever the previous number was, this let us leave that as a random variable. Okay. in the previous generation it was yi minus 1 times np. Okay. I am not making it specific times np, but now the np can come out, okay, because that is just, those are just parameters, numbers. So, they can come out by linearity of expectation. So, n times p times expectation of y I minus 1. Okay. So, what we have done is made an interesting jump in the sense that we have made one step of an inductive argument. Basically, what we are saying is, if we can represent the number of females in the previous generation by a random variable yi minus 1, the number of females in the current generation is going to be np times the expectation of yi minus 1. Now, what does this mean? And this we can remember, this we could do only because we understood, we took the time to understand this notion, the second notion of conditional expectation, and we claim that that notion of expectation of that notion has this left hand side idea. Okay. So, now so if you let us look at what you have done in the ith the expected number of females in the ith generation is np times the expected number of females in the previous generation. Okay. So, then it will be np the whole squared times the number of females in the grandmother generation, and so on. So, and what we know is at the very start of this branching process, we started with one female, and so y 0, if you will, actually this has to be a y 1, y 1 if you will is 1. At the end of the first I guess it depends on how you start counting the generation, but at the very beginning there is just one female. So, you can think of this as basically an inductive argument in which the base case is that initially you started off with one female. So, if you substitute, you are going to get the expectation of yi to be np the whole to the power I. We have basically understood, at least on expectation, this branching process. In this segment we studied the second notion of conditional expectation. We applied that to this branching process to understand this this question of the expected number of female rabbits after I generations. What we did importantly is we confirmed an intuition. We have an intuitive sense of how many expected number of females we will have in the ith generation. Now, we have a way to dot the i's and dash the t's and claim that our intuition is in fact rigorously correct. So, with that we conclude this segment. In the next segment we will be talking about geometric random variables, which we have already briefly talked about, and we will apply that to a very important context called the coupon collectors problem. And with that we will end this segment.